randomized box-ball system, and it's based on the many collaborations with Hamburg Liu and Masato Okado and Grégoire Miswich and Vincent Pasquier. I think he's chairing this session. Thanks, Vincent. So yeah, actually, I think many results, there are many results, but some of them derivation is not rigorous. It's a sort of thesis of derivation, but I think the obtained results are exact, supported by rather extensive numerical simulation. So let me, begin by recording the very original Takahashi Satsuma box ball system. So 99% of my talk will be concerned with this very original version. So we have the time evolution indexed by integer, non-positive integer L. L is the capacity of the carrier, and time evolution is induced by the carrier, and which is schematically shown like this, where the number on the horizontal edge is load of the carrier. It's a number of balls contained on the carrier. And this diagram is nothing but the combinatorial R of the SF2. And so this is an example of the time evolution. And so TL, for example, is TL is in the solvable lattice model language is a rho transfer matrix with spin L half auxiliary space at Q equals 0. So these aspects has been explained many times in this workshop, I think. Yeah, okay. And those time evolutions are commuting. And if you have consecutive k solitons enough separated from other things, then it will be a k soliton with, k soliton. It will be called k soliton. And the bare speed of k soliton without interaction without any other parts. And the dynamics TL is minimum LK. And the phase shift of collision of the I soliton and J soliton is twice minimum IJ. So schematically shown like this. So we have a conserved quantities, E1, E2 through infinity, expressed by this formula. So by the way, can you see the, my cursor on the screen? Can you see this cursor? Okay, thanks. So EI is expressed in this manner. So MJ is a number of J soliton contained in a state. So if you draw the Young diagram, and so with J length, J loss with multiplicity MJ, then this EI is schematically seen as the number of boxes contained in the first I columns, although in this picture it says EJ. So the first J column total number of box is EJ. So EJ is a kind of area. And the simplest example is E1, which is the total number of solitons, and the E infinity, it's a number of ball. And by conserved quantity, I mean that this holds for any pair of I and J. So as you see that these energy data and this MJ data, as you can see from this data, they are equivalent. So energies specify these areas. The MJ specifies these multiplicity of the blocks or kind of, blocks in this diagram. So these are the equivalent data. So generalized Gibbs ensemble. So it's formally like this, partition function is formally like this. So it's a configuration sum with many temperatures, actually infinitely many temperature in general, and L is a system size. And so you can argue that this is configuration sum can be replaced by the summation over soliton contents. And given specified soliton contents, number of the states having the same soliton contents is given by this fermionic formula that I talked yesterday. So this kind of not the exact equal is, so I said that this formula refers to the so-called highest states. So there are actually the contribution from non-highest states, but those contributions are kind of not dominant, or they are not relevant in certain L infinite limit when we consider such sort of limit. So in that sense, this is similarly equal, but so you can effectively replace this summation by this formula. I is the number of I soliton, as I said. And PI here is upper bound of this fermionic exclusion rule. And that's a so-called number of I hole and this is L minus twice EI. It's also called vacancy. And the free energy per site is given by this formula. So by randomized box-ball system in this talk, I mean the following. So the randomness is enters in the ensemble of the initial states. So the dynamics of the BBS itself is, of course, deterministic. So the randomness enters by ensemble, by choosing a certain ensemble of the initial states. And probably 99% of my talk will be concerned with the IID distribution of balls with VST Z. So the relative probability of having the empty site is empty site, and one ball field site is 1 versus Z. So the ball density is Z over 1 plus Z. So that means, so among those infinitely many temperatures, I only retain this part because this infinity refers to the number of balls. So all the other inverse temperature is formally 0, except, formally 0. And I only retain this variable, fugacity parameter. And I also stay within the so-called subcritical domain where the density does not exceed 1/2. And so although I concentrate on this situation, but some results are known or available also for multi-temperature GG, but I won't mention. So let's do the thermodynamic Bethe ansatz. So in the thermodynamic limit where L goes to infinity, so I assume that this number of solitons and number of holes scales linearly with respect to L. So this is a kind of extensive quantity, so it's natural to assume this. This is sort of part that the derivation of the physicists. But the result is perfectly matches with simulations. So let me just allow to speak in that manner rather slowly. But anyway, so PI, this vacancy was this formula. So if we divide both sides by capital L and take this scaling limit, then I have the equality between hole density and the string density. Well, this MJ, in my yesterday talk, I explained that this is the number of the length J strings, or J string. So this, if I divide it by L, so this low I becomes the string density with length I here. So this is a kind of string hypothesis translation of the Bethe equation, I would say. So it will be used later. And equilibrium free energy is given by per site are given by taking the minimum of this quantity. So I apply the starting formula, starting formula to this. So this now becomes L times rho I, and this becomes L times sigma I. So I expand this by starting formula and then took the log. And due to this assumption, this capital L disappeared. So the problem is to find the minimum of this quantity under this constraint. And that calculation is rather standard kind of routine work. So I take this, I consider this equation and end up with this algebraic equation plus this kind of boundary condition for this combination, which I call yi. So somehow, interestingly, that this condition not kind of is expressed only by this combination. So this yi will play a very important role in the later part of my talk. So by the way, this algebraic system, somewhat looking attractive, has very deep origin. So it's an algebraic form of TBA equation called Y system. So usually TBA equation is an integral equation, including spectral parameter, but this can be regarded as a very special designated limit of that, so-called constant Y system. And it has been formulated for any affine D algebra, and many results also from cluster algebra theory is now available, but I won't talk about that. Anyway, so the problem is to find this solution of this equation with this boundary condition. Observe that this is a second order difference equation, and I have two initial conditions. One initial condition and one kind of final condition. So then it should fix the solution uniquely, and here is the solution. So the solution is yi here, and sigma I is given, and rho I is of course given by, once you know the yi and sigma I, rho I also fixed. So recall that I had the expression of the vacancy like this, and I divided both sides by system size capital N, took the scaling limit like this. So EI, this little EI is capital EI divided by, and with L going to infinity, the limit, density of the EI. So somehow I'm taking the vertical 1 over L scaling of this Young diagram. So depth of this ice column in that scaling limit should be, so because this capital EI while L going to be little EI, so this should be little, sorry, this area should be little EI. So the depth of this red kind of strip is obtained by taking the difference like this. And because of this equation, so it can be computed by this combination, and the result is this. So I think this result is essentially due to Han and collaborators software set to case. So equivalent limit of the shape of the concept Young diagram. So this is a SL2 case. So this is a slightly kind of digression to the higher rank case. So it's a kind of remark. So there are nth probe Young diagram concept Young diagram, as I said yesterday. And let's look at the eighth Young diagram, and let's consider the depth of its ice column and take its scaling limit. Then the result is expressed by this ratio of the Schur function with rectangular shape, where the entry is as a fugacity of the color eyeball and so on. So this result was mentioned also in Han's talk yesterday, and he made in his talk, I think, row and column ups are kind of switched. So he obtains that he uses a transpose convention. So I'm sorry for changing the convention. But so according to him, this scaling limit is rather easy. Actually, I think so. And the more challenging kind of low scaling in this manner. And it was logarithm as he explained. And but yeah, this is just a remark. So this is, I think, the result by Masato and Han and myself. Anyway, so as I said, so we had to check by numerical simulation. So this simulation I did, so rather kind of, so as you know, I don't have much simulation skill, so it's not very so extensive. But so this blue plot is simulation data BBS. So I generated probably thousands samples or something like that. I don't remember. And this orange curve is a TBS theoretical prediction. So yeah, the agreement is not so bad. So this is the SL3 case. So the higher rank case, it's a kind of digression. So now let's come to the generalized hydrodynamics. So it's a kind of very active subject initiated by people like Castro, Alvarado, and Doyon, Noshimura, Nardis, many collaborators. I think Benjamin is also in the audience, I suppose. So so let's assume that this string density and hole density and Y variable are space-time dependent. And there are two basic ingredients. The one is speed equation, and the other is continuity equation. And combining them, we will get the separated equation on Yi. So as I predicted, so Yi plays a very important role of normal mode. So let me first explain the speed equation. I think this actually already appeared in the talk yesterday. So, so in my description, the dynamics is always has got the index L, TL. So this TL, everything has TL dependence, but it's messy, so I often omit the L dependence. So this quantity actually means L dependent. But remember that this low sigma and Y, they do not depend on L. But the velocity depends, of course, the dynamics, capital L, sorry, little L. So it depends on little L. So here is the speed equation. So the denormalized or effective speed is bare speed plus some interaction effect. And probably you see how we should set up such equation by using, by looking at these equations. I think there are already the explanations, so I won't add any more explanation anyway. So, so this contains a minus and many, maybe 4 terms and so on. But if I combine it with a Bethe equation, which this one. then it simplifies rather considerably and like this. So here you see that this equation can be described by combination sigma times v with extra variable here. The other things are all numerical. So let's write it in the matrix form. So speed equation in matrix form is like this. So this sigma star product v is this combination column vector. And M is a matrix of S matrix of solitons, and Y is the diagonal matrix with entries Y variables. And this kappa is this column vector. And in this notation, Bethe equation also written like this. By the way, this kappa 1, we set L1 here. So all the components are just 1. So, but yeah, for uniformity of the convention, I use the notation kappa 1. So basically, I can solve this combination by inverting this matrix, and I can solve this sigma by inverting this combination, so which I wrote in this manner. So this is a division, component-wise division of the infinite column vector. The important thing of this formula is it's thoroughly expressed by these Y variables. So these kappas are just numerical, and M is also numerical. So they are thoroughly expressed by Y variable. That's the point. So, and now if I substitute the result of the Y's for the homogeneous case, then the result has this formula where I probably shouldn't have this. So if you set A equals Z here, then that will be the result. So this is a slight generalization to the two temperature GGE case. So if I specialize A to the Z, then this is the answer. So this is the result of the homogeneous system. By the way, while deriving this formula, we also found this formula with Gregoire and Vincent. And I think that this formula, I do not see it in any other literature. So maybe it has some interesting meaning anyway. So let's move on to the continuity equation. So I consider the conservation of the Hall current, or holes. So this is the I Hall density, and this is the I Hall current density. So this is a continuity equation. But as I explained, this is, so if I denote the inverse of this matrix by G, then this is nothing but a G kappa 1, and this is nothing but G kappa L. And again, everything, maybe not everything, but T is TL dynamics. So this TL dynamics, and this VI is effective velocity and the TL dynamics. So if I do this differentiation using this elementary formula, then there are many common factors in the resulting equations. And also this combination is nothing but the sigma, and this combination is nothing but the sigma times V. So there are many common factors. And if I remove them, so I got this equation. So this V comes from this extra V factor here. And you see that this is certainly separated. I mean, separated only one I. See? So that it was split into solitons of each level. So the most fruitful application of this separated mode equation is so-called Riemann problem in the general hydrodynamics. So it's a problem to describe the profile of the fluid, starting from the homogeneous initial condition, except one simple discontinuity. So it's also called partitioning protocol, and it has been a very popular setting in the recent literatures. So we did this analysis. So what we did, so at the initial, at t equals 0, we prepared state in this inhomogeneous. Here is no ball here. And from the origin to the left side, we prepare the system in the IID distribution of balls with density P. And let it evolve under the dynamics T infinity. So of course you can take this little L, but yeah, for simplicity, let's consider T infinity. And what happens? So it happens like this. You have this kind of density plateau emerge. This density plateau broadened linearly in time T. So the plot against R over T, so-called Ray variable, collapses into a single curve like this. So this single curve is kind of universal because all the T effect is accumulated to this diagram. So it's a fundamental problem, basic problem to describe and determine this height and position of the case plateau. So by the way, so why this kind of plateau emerge? So that's a basic question. So this is kind of explanation. So I didn't mention too much, but this amplitude, effective velocity is increasing function with respect to I. So even the effective velocity is okay. So the smaller solitons is slower and the larger solitons are faster. Do I have a question, by the way? Is it okay? Can I continue? So the smaller solitons are slower. So in this region, the amplitude one soliton hasn't reached it. So we lose the amplitude one soliton, while there are every soliton here. And here, so it's more distant. So the first slow two solitons of amplitude 1, 2 are missing and so on. So these larger solitons are faster, so they can indeed reach such distant region from the this boundary. So that's what's happening. Now, so to this problem, I approach in 2 steps. The first, I make the ballistic approximation. And that will determine this hk height and position zeta k. By the way, so this, as I mentioned, this density p and fugacity z is related by this formula. So that gives us position and height of the plateau. But actually, this plateau has diffusive broadening, and that will be described by by taking the diffusion effect into account. So the first step is a ballistic approximation, by which I mean that this space-time dependence only comes through this combination, Lie variable z. Then separated equation, if I use this fact, becomes like this. So this is a kind of very strange or singular equation. So that means if zeta is not vi, yi must stay constant. So if it's a left side of certain vi, then it must equal to the left infinite value, and if it's greater than vi, if it must be equal to the rightmost values, if we assume that it only changes once. But if you see that this diagram, it's obvious that it can only change once. So because of this constraint or kind of information, so we can understand what's happening like this diagram. So in the first plateau, every soliton is contributing. But as I said in the maybe zeroth plateau, in the first plateau, we lose the slowest soliton, the contribution y1. So this y vector should be replaced by this vector, where y2, y3 are the original values which I obtained in the homogeneous setting and so on. So these y vectors with missing first components will be denoted by this symbol. And I already explained this notation b. So this b was here. So you see that this is only determined by y vector. So if I use this y vector, substitute this y vector, then I can derive everything. So for example, this position is the place with this discontinuity happens, or zeta becomes vi, so it can be determined in this manner. And also the height is the total number of balls, so it's computed like this. So the result is given like this. So I said that we consider the T infinity dynamics, but this game can be played for TL dynamics, and for this TL dynamics, the position gets modified by this factor. So this is the result, and this is a comparison with the simulation with 50,000 samples. So this orange plot is the simulation results, and this dotted lines up GHD predictions, and agreement is rather good. But as you see that plateau H's exhibit broadening, which may be viewed as a finite T effect, so how to deal with it. Actually, I was working on that maybe 2020 in February, and in Canberra Baxter's conference was there, and I was learning. I was asking a lot of questions to Benjamin about the calculation and those things. Anyway, so the analytical description of the diffusive broadening of the plateau edges. So this is a zoom in the softening or broadening of the plateau edge. Yeah. And so there should be some diffusion effect. So So on general grounds, we expect such sort of corrections. And the problem is to determine this diffusion constant. And there's some theory and paper and literature to determine how to do that by using TBD and GHD. And we did this calculation. So I cannot explain the detail, but the result is naturally expressed by the complementary error function like this. This is basically a function like this, extrapolating this value here and this value here, and so on. So the problem is to determine this diffusion constant, CLK. And this is the result. So if we scale this plot in terms of this variable, then every plot should collapse into a single curve. And here is such plot. So the agreement is rather good. So that's the analytical description of the diffusion. So this is more recent work and about the general currents. So let me introduce some generalized currents. I'm sorry about this symbol or notation. So usually probability theory people, this eta means the local state 0, 1. Yeah, so we somehow, I'm not sure, mistakenly, I'm not sure, use this notation to mean different things. So this is a current of energy EJ under the time evolution TL. So normally people consider that some density with some time evolution, but normally, I mean, in non-integral situation, only one kind of time evolution. But BBS, you can implement very easily many kind of type of evolution, and you can look at many kind of densities. So we can make use of, take advantage of that sort of things. So we consider the current of energy EJ under the time evolution TL. And this quantity is a local quantity of this at position X. So how can you practically calculate it? This is a rule. So this look at the X position from the left coordinate X position like this, and look at the load of the carrier here. And suppose that it is U under the time evolution TL. And the next step, U prime under the time evolution EJ. Then this is the result. So this is due to crystal theorem, that sort of things. But yeah, this is how practically we can very elementary calculate this quantity like this. That sort of thing is a kind of advantage of a DBS. So we can compute everything very concretely and elementary. And there is some interesting symmetry that this quantity is symmetric with respect to interchange of L and J. So here it demonstrates the equality like this. So this here, first I consider T3 time evolution and then T2 equation. Then I'm getting this quantity. And that's shown in this letter. And here, the opposite indexing, I obtain this letter. And if you compare these red letters, upstairs, downstairs, they are the same. So this is a demonstration of this equality. So this is general currents. So mean values in the homogeneous system, it can be easily calculated. So yeah, I want to use this quantity result. But the important thing is that some maybe the correlation there things. But before going to the correlations, let me mention some well-known special cases. For example, if L is 1, then if you look at this formula, so V1K is always 1. I didn't mention it, but the effective velocity is always 1 for the T1 dynamics. T1 is actually the kind of one-side translation. So every soliton travels with velocity 1. So this is the energy, the density of the energy EJ itself. And further, you specialize K to 1. Then this minimum disappears, and you count the total number of soliton density. And if I take K infinity here, so then you have this formula, and you get ball density. And TL infinity is a ball current under TL current because I have velocity factor here. See, so this certainly depends on L. Now this is a bit complicated part of my talk, but I introduced the time average correlations containing 5 indices. Sorry, so 4 is a rather straightforward. So it's a correlation of MI current and LJ current. But because this is BBS, the problem is, by the way, this is a space spatially integrated by this summation X, and this is a connected correlation. And by taking this one, I mean the time average with respect to the Tn dynamics. So that's the reason we should have 5 indices here. See, so n specifies the dynamics, index t and dynamics. And the other 4 index naturally comes from this double index current. And so naturally, we can expect that this time average is replaced by this quantity, but it has been well numerically confirmed. So we assume that. And also based on the numerical simulation, we conjecture that this nasty 5 indices reduced to the 4 indices. So it becomes independent and independent for n greater than minimum mn. So somehow for n large, so this certainly depends on the 4 indices coming from the current. At the moment, we don't have the proof, but some physicist argument why it has to be so. But anyway, so let's let me point out some special cases. So if I specialize m and L1, then this becomes this reduced to this quantity. And because, as I mentioned, this is a ball correlation, it's nothing but this. And if I take other one of the index to capital L, then I have ball current correlation. So I'm using the previous page's identification. So yeah, I use this. So this is a ball and current correlation. And you can show that this equals to the second cumulant of NT. What is NT? It is a number of balls passing through the origin during time interval 0 and t. And if you take this fluctuation, then it should scale linearly in t, and this coefficient is the second cumulant. So this should be very important quantity. And if I take one further index to L, then I get the true weight, which is a correlation of current and current. So this generalized family of the correlation contains many interesting and important and basic transport characteristics. And but so we can treat this more general case at the same time by using TBA analysis. So we can evaluate it exactly by TBA. So how it goes. So so first, so this correlation should be calculated in this manner by using the fluctuations. And so we need this fluctuation, but this can be found by considering the free energy Hessian of the free energy Hessian computed by TBA, which was done using the TBA free energy that I explained several pages before. And the result is known this. By the way, this sort of result goes back to Yan paper in 1969. Yeah, so we still use Yan paper results in some sense. And so this can also be shown by direct calculation. After plugging all these results into this formula, we find this final form in some sense. So the very remarkable fact is this is completely symmetric with respect to the 4 indices. So as I said, that the exchange of M and I and L and J are automatic, but other exchange symmetry is quite non-trivial. So yeah, it's kind of interesting and curious. And here is a numerical simulation for that. So this is C36N and this IGN sufficiently large versus N. So this N, when N satisfies this equality, it should converge to an N independent quantity. So this value, theoretical value obtained by this formula is plotted here. And certainly if N is 1, 2, and 3, so if N is greater than 2, it agrees with this one. So the final, I plug the result for the effective velocity for the homogeneous system to this quantity. So that's the result, numerical result. But for some choice of index, we can find a very close formula in terms of fugacity to this, but I omit them. So typically the simulation is bound by 1 million samples and so on. So this is kind of final topic. So that's the scaled cumulant generating function. So we consider this quantity where NT is the number of balls passing through the origin during the time 0t. And we take this, compute this. So if things are normally scaling, so we should get this sort of cumulant expansion. So Cn is the nth cumulant. And the result is this expression for TL dynamics. So I didn't write derivation, but some expert probably in the audience know it very well. So what we do is we differentiate this quantity by lambda and then get very non-trivial differential equation with respect to this lambda. And to integrate this differential equation with proper initial condition, we get this quantity. So that's the result. So it's pretty simple and kind of pretty expression. And yeah, so this is one result, but to compare with the experiment simulation, maybe it's a good idea to further proceed to the large deviation rate function. So that's the Legendre transformation of F lambda, which I call GJ. And then the probability of NT, probability of taking NT is expressed by this formula. So that's a kind of a general story about large deviation, general things, large deviation. So we take the Legendre transformation of a scalar Legendre function and then the large deviation. So, so here is a comparison with the simulation. So this blue plot is for time t 4000 and red plot is time for the 400 and 2000 and the ball density 0.3 and the T10 dynamics and about million samples. So the J, the meaning of J is an average current. So normal, of course, we expect that this NT is growing linearly with respect to T. So the NT divided by T is the mean current. So this axis is the mean current, and this current mean value is 0.749. and the cumulative value is 1.30. And those dots are the simulation results, and these curves are the theoretical predictions. So the vertical axis probability NT normalized by the maximum value. So the largest value is 1. So here it takes the largest value and it rapidly decreases when the things gets largely deviate from the average. That's what figure is saying. But even encouraging for us is the discrepancy of these two. So what does it mean? So this plot, can you see my cursor? That the magenta curve is just a naive Gaussian fit using this cumulant and average value. See? So this is just a Gaussian plot. But actual result of the simulation follows, deviates from it, and it follows this large deviation function G lambda. So somehow this accuracy of this description is kind of demonstrated in this plot. That's a result. I think I'm almost done, but yeah, let me finish with just a few comments about complete BBS. So as I introduced yesterday, so there are a new version of the multicolor BBS, which we call complete BBS. So all the soliton has a diagonal scattering. That means it doesn't change the phase. So if this is the length of soliton, the output also for soliton this has exactly the same form. Also, you have the very messy intermediate states. These are soliton, 3 solitons, length 3 soliton. Sorry. So our naming is S13. So 3 certainly refers to this amplitude of soliton, and 1 to 4. So S24. So this 4 refers to the length of this soliton, and this upper indices refers to the certain color of the soliton. But the point is, all the solitons are not labeled just by 2 indices. That's a remarkable simplicity of this complete BBS. And we did similar domain work problem, and these green plots are the simulation results, and the red curves are the theoretical prediction, GHD theoretical prediction, which agrees very well. And also the diffusive broadening of this fit, yeah, like this. So for example, this fit has been computed by system size about million and time duration about 1,000 and samples at 100,000. So how to say? 100,000, 0.1 million anyway. So in total, we the simulation, the computer has applied 10 to the 14 or 15 times of the combinatorial R of the rectangular crystals and so on. So it's rather massive calculations. And I think Gregoire once used the supercomputer in Sacre. So yeah, let me finish with some questions. So this is GHD for BBS, which was rather successful. But of course, you are more familiar with the naive or the original version introduced by Takahashi-san 93. So that's usual n-color BBS. But so this is a typical 3-soliton scattering. I'm sorry that I changed the background from 0 to 1. Anyway, so this is scattering 3 solitons like this. So as you see that solitons changes its internal labels like quarks in hadron collisions. So they interchange UD quarks and so on. So it's similar things happening here. So, but nevertheless, we come back with exactly the same list of the amplitudes. So we are happy, but somehow soliton has changed the phase. See, so internal label has been interchanged. So in that sense, I would call that this kind of PBS is not, doesn't have diagonal S matrix. Then how to set up the speed equation when the solitons change its phase by collisions. So we may have this kind of effect velocity variable and so on corresponding to this initial state, but in the final state, we end up with this kind of variables. Then how to set up this speed equation, effective speed equation? It should contain combinatorial and that sort of things. That should be pretty interesting. And I tried several possibilities, but without success. So I think this is outstanding problem. So yeah, actually, as this is almost the end of my talk, and but I think this afternoon, Ban-san will also talk about further progress. I think his talk is the very last talk in this workshop, so it's kind of grand finale, and I very much look forward to his talk. And using this opportunity, I would like to thank the audience and also the organizers. So thank you. This is the end. Somehow I don't hear anything from.
Test.
Yeah, I can hear.
Oh, you can hear us?
Yeah. Now I can hear you.
Wow.
Yeah, hi. So concerning the non-diagonal scattering,
Yeah.
I mean, this is something that occurs in a quantum system, like in sine Gordon, for instance, where you have indeed internal indices that exchange on the scattering. So it's not diagonal.
Yeah.
So, but people know how to do the TBA for that by this nested Bethe ansatz method, where you kind of diagonalize, you do a Bethe ansatz for the internal indices in addition to the positions of the solitons and all that. So surely something similar can be done here, and from that one can calculate the currents and in principle everything.
Yeah, I agree. So yeah, at the level of TBS, so-called higher level equation ansatz, yes, it has been done. But so I think similar things should be done for speed equation. Yeah, that will be a very interesting challenge. That's
yes, speed I understand. But in principle, one can get at least in a indirect fashion the speed equation by using TBA and then calculating the currents within TBA, which one can do. Which is relatively, I mean, it's done in sine Gordon and other non-diagonal scattering theories. And then from that, you kind of extract the effective velocity. But yeah, I mean, I understand your question. Like, do it more directly, that could be interesting.
Yeah. Do you mean you can know the effective velocity without setting up the speed equation, but only using the TB equation and so on?
Yes.
Oh, I see. That's interesting.
Because you can evaluate the currents using TBA, essentially using TBA. Yeah. And in the end, it's a bit complicated because the degrees of freedom that come out are maybe linear combinations of the basic, at least in the quantum system. In this case, I don't know. Okay, just a comment. Thank you.
Thank you. Yeah, but still, I would like to set up the consistent speed equation which contain the changing solitons.
I think it's a little more subtle than just applying, because you see the solitons, they are very complicated now. They carry numbers. So more yeah, but it's okay. I mean, we have to see. We have to.
Yeah, I wish I was there.
Thank you very much. So use in some part the inverse of the matrix I plus my, I think. So to obtain the effective velocity or something.
Yeah.
So yes, yeah, the next slide. Yeah, yes, maybe here. So, and this inverse map is so mathematically, I think it's not obvious that we can define or so.
Yeah. So yeah, actually this yi, yeah, you are right. So this yi inverse can become subtle if yi is not decreasing rapidly enough. But so actually what we use is the result here. So this zi is from between 0 and 1. So this zi is geometrically decreasing. Then that allows us to take this, make this inverse well defined, and we can check numerically as well. So I can, for example, this is infinite matrix, and we can truncate it in finite size, let's say 50 or so on, and numerically inverse. That's very kind of shows stable behavior. So that's inverse is kind of well defined. Actually, so this sort of formula kind of also, yeah, kind of indirect indication of that procedure is actually justified.
But this will give us one solution somehow. But so invertibility is a bit more strong, I think.
Yeah, you are right. So if I do not use this specific or concrete results, I don't know what happens. So maybe it will lead to some other interesting, features.
Okay. So depend on the GGE.
Yeah. So depend on the GG.
Depend on
But,
GG.
as a physicist, I naively expect that for any GGE, maybe let me refrain from.
So GGE will have enough decay, you think?
Yeah, I think so. Yeah. So for higher rank case, it was okay.
Yeah, no, you also, I mean, we also checked it with, we can put a second parameter, A, which is just the number of, counts the number of solitons. I mean, some kind of, but it's difficult then to put more parameters in such a, okay, well, I mean, just for the sake of asking question, you define the quantum model. So do you think something like that could be used for the quantum model which you introduced?
You mean the one I talked yesterday?
Yes, of your talk of yesterday.
Oh, yeah. As I said, many things yet to be explored. So I have no idea at the moment.
I was guessing
maybe
the answer would be that. Okay. Okay. Well, then, thank you very much for this very nice talk.
Thank you.